Can you hear me? I am delighted to receive the Innovation Luminary Award for Innovators' Courage. Cambridge University has been at the center of research and innovation for over 800 years, helping drive the world and society forward. I am happy to have been a part of it. So let me begin my lecture. In Viking mythology, also written about 800 years ago, two wolves Skål and Hati chase the sun and moon. When the wolves catch either one, there is an eclipse. When this happens, the people on Earth rush to rescue the sun or moon by making as much noise as they can, in the hope of scaring off the wolves. There are similar myths in other cultures. But after a time, people must have noticed that the sun and moon soon emerged from the eclipse, regardless of whether they ran around screaming and banging on things. After a time, they must also have noticed that the eclipses didn't just happen at random, they occurred in regular patterns that repeated themselves. Despite some early success predicting the motion of celestial bodies, most events in nature appeared to our ancestors to be impossible to predict. Volcanoes, earthquakes, storms, pestilences, and growing toenails all seem to occur without obvious cause or pattern. In ancient times, it was natural to ascribe the violent acts of nature to a pantheon of mischievous or malevolent deities. Calamities were often taken as a sign that we had somehow offended the gods. The human capacity for guilt is such that we always feel there is something we should have done, or not done. These regularities were most obvious in the motion of the heavenly bodies across the sky. So astronomy was the first science to be developed. However, early Christian thinkers rejected the idea of natural laws. Indeed, in 1277, Bishop Tempere of Paris, acting on the instructions of Pope John XI, published a list of 219 errors, or heresies, that were to be condemned. Among the heresies was the idea that nature follows laws, because this conflicts with God's omnipotence. Interestingly, Pope John was killed by the effects of the law of gravity a few months later, when the roof of his palace fell in on him. Despite the hostility from parts of the Christian Church, it was gradually realized that the laws held in other areas, as well as astronomy. This led to the idea of scientific determinism, which seems first to have been publicly expressed by the French scientist Laplace. I thought I would like to quote you Laplace's actual words, so I asked a friend to track them down. They are in French, of course. But the trouble is, Laplace was rather like Proust, in that he wrote sentences of inordinate length and complexity. So I have decided to paraphrase the quotation. In effect, he said that if at one time we knew the positions and speeds of all the particles in the universe, then we could calculate their behavior at any other time, in the past or future. There is a probably apocryphal story that when Laplace was asked by Napoleon how God fitted into this system, he replied, "Sire, I have not needed that hypothesis." I don't think that Laplace was claiming that God didn't exist. It is just that he doesn't intervene to break the laws of science. That must be the position of every scientist. A scientific law is not a scientific law if it only holds when some supernatural being decides to let things run and not intervene. The idea that the state of the universe at one time determines the state at all other times has been a central tenet of science ever since Laplace's time. It implies that we can predict the future, in principle at least. In practice, however, our ability to predict the future is severely limited by the complexity of the equations, and the fact that they often have a property called chaos. This means a tiny disturbance in one place can cause a major change in another. A butterfly flapping its wings can cause rain in Central Park, New York. The trouble is, it is not repeatable. The next time the butterfly flaps its wings, a host of other things will be different, which will also influence the weather. That is why weather forecasts are so unreliable. Ever since Laplace's time, we have been searching for a complete set of laws that would fully describe and determine the universe. We have had false dawns before. At the end of the 19th century, it was thought that everything could be explained in terms of transport coefficients, like electrical resistivity and heat conductivity. All that was necessary was to measure these quantities to fulfill Laplace's dream of a complete set of laws governing the universe. The discovery of atomic structure and quantum mechanics in the early 20th century put paid to that hope. Again, in the 1930s, Max Born told a group visiting Göttingen, "Physics as we know it will be over in 6 months." This was shortly after the discovery of the neutron, and it was thought that it, the proton, and the electron were the only elementary particles. However, this did not explain radioactivity, and a whole zoo of other subatomic particles were later discovered. The force of nature can be classified into 4 categories. In order of increasing strength they are the gravitational force, the electromagnetic force, and the weak and strong nuclear forces. This division of forces is phenomenological, based on their strengths and interactions, and may not reflect their origins. Ultimately, one might hope to find that they were all different aspects of a single force, in some unified theory. So far, our attempts to find this unified force have met with rather limited success. The electromagnetic and weak forces were unified in the Salem-Weinberg theory, but the strong forces appear to obey a separate theory, called quantum chromodynamics or QCD. Various theories have been proposed unifying Salem-Weinberg and QCD, but none are supported by experimental evidence. The big problem, however, is to unify the electromagnetic, weak, and strong forces with gravity. This is because general relativity is what is called a non-renormalizable theory. What this means is that most quantities one calculates in quantum theory are infinite. The same is true for the other 3 forces, but in their case one can absorb the infinities in a redefinition, or renormalization, of quantities like masses and charges in gravity. However, the infinities can't be so absorbed. Instead, one has to make an infinite number of undetermined quantum corrections at high energies. This would be the end of Laplace's dream of scientific determinism, a complete set of laws governing the universe, from which one could predict the future. How to solve this problem has been the main focus for research in theoretical physics over the last 50 years. One possible solution would be supersymmetry, a possible symmetry between force-carrying particles, like the photon, the particle that carries the electromagnetic force, with matter particles, like the electron. Supersymmetry would cause many of the infinities of quantum to cancel, but it is not known if there is a theory in which they would all cancel. It's a bit like a drunk looking for his key under the lamp post, because that is the only place he'll find it. Supersymmetry may not be the answer, but it's the only idea we've had. So far, at least, there is no experimental evidence for supersymmetry. For the purposes of this lecture, however, it doesn't matter exactly what the unified theory is, as long as there is one. If there weren't, the universe wouldn't be ruled by science, but would be arbitrary and unpredictable. But even if we find a unified theory, it is only a set of rules and equations. As I asked in my book, A Brief History of Time, what is it that breathes fire into the equations, and creates a universe for them to describe? In the words of the Hitchhiker's Guide to the Galaxy, this is the ultimate question of life, the universe, and everything. In the Hitchhiker's Guide, they built a giant computer, Deep Thought, to answer this question. 7.5 million years later they returned to hear the answer. Unlike the Hitchhiker's Guide to the Galaxy, I don't think the answer is 42. The ultimate unified theory doesn't define a single universe, because of the uncertainty principle of quantum theory. Instead, the theory defines correlations between quantities. That is the probability that B occurs if A does. These correlations can be calculated and stored by a computer. Thus, like universes can exist from an abstract set of correlations. From these correlations, the computer could reconstruct a picture of the universe, rather like human beings are images projected by computers in the film, The Matrix. What are the universes the ultimate theory predicts? To answer this, one needs to know what happens at the beginning of the universe. Most scientists agree that the laws of science hold elsewhere in the universe, but they are vague about whether they hold, or can even be defined, at the beginning of the universe. But unless we know what happens at the beginning, cosmology has no predictive power. All cosmology can say is that things are as they are now, because they were as they were then. In order to have a definite boundary condition at the beginning of the universe, Jim Hartle and I put forward what is called the no-boundary proposal. Basically, this says that the beginning of the universe is a regular point of space-time, albeit in the Euclidean, and that the laws of science hold there with finite, though complex, matter fields. The no-boundary proposal implies that cosmology is given by what is called the wave function of the universe. This will be described in more detail by Thomas Hertog on Thursday. The history of the universe depends on the values of a scalar field at the beginning of the universe. If this field is low, the universe would never expand to its present size. But if the field is above a critical value, the universe will undergo what is called inflation. It grew at an ever-increasing rate, like the way prices go up. The world record for monetary inflation was in Hungary in 1946, when prices rocketed by 41.9 quadrillion%. Here is a picture of 100 quintillion pengo note, the largest banknote ever issued. But the hyperinflation in Hungary was nothing compared to inflation in the early universe. The universe expanded by a factor of at least a quadrillion in a tiny fraction of a second. Unlike inflation in prices, inflation in the early universe was a very good thing. It produced a very large, ununiform universe, just as we observe. However, it would not be completely uniform. Quantum fluctuations in the early universe will make the inflationary expansion irregular, as Markmanov, Starobinsky, and I predicted. The early universe will therefore be slightly non-uniform. These irregularities would produce small variations in the intensity of the microwave background from different directions. The microwave background was first observed by the Kabi satellite, and later in more detail, by the WMAP and Planck satellites, and was found to have exactly the kind of variations predicted. So we know we are on the right lines. The irregularities in the early universe will mean that some regions will have slightly higher density than others. The gravitational attraction of the extra density will slow the expansion of the region, and can eventually cause the region to collapse to form galaxies and stars. So look well at the map of the microwave sky. It is a blueprint for all the structure in the universe. We are the product of quantum fluctuations in the very early universe. God really does play dice. The beginning of the universe itself in the hot Big Bang is the ultimate high-energy laboratory for testing the ultimate theory, and our ideas about the building blocks of space-time and matter. Different theories leave behind different fingerprints in the current structure of the universe, so astrophysical data can give us clues about the unification of all the forces of nature. There are many ambitious experiments planned beyond Planck. We will map the positions of billions of galaxies, and with the help of supercomputers, like COSMOS, we will better understand our place in the universe. Perhaps one day, we will be able to use gravitational waves to look right back into the heart of the Big Bang. Most recent advances in cosmology have been achieved from space, where there are uninterrupted views of our vast and beautiful universe. But we must also continue to go into space for the future of humanity. I don't think we will survive another 1,000 years without escaping beyond our fragile planet. I therefore want to encourage public interest in space, and I've been getting my training in early. So let me finish by reflecting on the state of the universe. It has been a glorious time to be alive and doing research in theoretical physics. Our picture of the universe has changed a great deal in the last 50 years, and I'm happy if I have made a small contribution. The fact that we humans, who are ourselves mere collections of fundamental particles of nature, have been able to come this close to an understanding of the laws governing us and our universe is a great triumph. I want to share my excitement and enthusiasm about this quest. So remember to look up at the stars and not down at your feet. Try to make sense of what you see and wonder about what makes the universe exist. Be curious. And however difficult life may seem, there is always something you can do and succeed at. It matters that you don't just give up. Thank you for listening.